Imagine you're floating in space near a black hole. You wave at your friend who's watching you from a safe distance. From your perspective, everything feels normal. 1 second passes, then another. But to your friend, they see you waving in extreme slow motion. What feels like 1 second to you takes minutes, hours, maybe even years for them to witness. Now flip it around. You look back at your friend and watch them age and fast forward. Days fly by in seconds. Years pass in minutes. The entire universe seems to be racing ahead while you're stuck in slow motion. This isn't science fiction. This is what Einstein's equations tell us actually happens near a black hole. Time doesn't flow at the same rate everywhere. It bends, it stretches, and near these cosmic monsters it breaks down in ways that challenge everything we think we know about reality. Today, we're delving into one of the most fascinating concepts in physics, how black holes warp time itself. We'll explore why time slows down near the event horizon, whether you could actually travel to the future, and the mind-bending possibility that black holes might allow time to flow backward. Because understanding black holes isn't just about space, it's about understanding time itself. Let's get into it. Before we can discuss how black holes affect time, we need to understand what time actually is, because, spoiler alert, it's not what you think. Most of us imagine time as this universal constant, a cosmic clock ticking at the same rate everywhere. 1 second on Earth equals 1 second on Mars, in another galaxy, everywhere. Time flows the same for everyone, right? Nope, completely wrong. Einstein figured this out in 1905 with his theory of special relativity. Time is relative. It flows at different rates depending on how fast you're moving and how strong the gravity around you is. This has been proven over and over. Astronauts on the International Space Station experience time slightly slower than we do on Earth because they were moving at 17,500 miles per hour. When they return after 6 months in orbit, they've aged about 0.0-0-7 seconds less than the rest of us. It's tiny, but it's real. Your GPS wouldn't work without accounting for this. Satellites experience time differently than we do on the ground. And if we didn't correct for it, your navigation would be off by miles, so time isn't fixed, it's flexible. It can stretch and compress. And nothing stretches time more dramatically than a black hole. Alright, what exactly is a black hole? The name is kind of misleading because it's not actually a hole, it's an object. An incredibly dense object with gravity so powerful that nothing can escape it, not even light. Here's how they form. Take a massive star, at least 20 times the mass of our sun. When it runs out of fuel, there's nothing left to fight gravity. The star collapses. All that mass gets compressed into a smaller and smaller space until it reaches a point of infinite density called a singularity. Around this singularity is the event horizon. This is the point of no return. Cross that line and you're not coming back, ever. The escape velocity exceeds the speed of light. And since nothing can travel faster than light, you're trapped forever. Now here's the key thing. Gravity doesn't just pull objects toward each other, it warps space-time itself. Think of space-time like a rubber sheet. Put a bowling ball on it, and it creates a dip. That dip is what we experience as gravity. A black hole is like putting something infinitely heavy on that sheet. It doesn't just create a dip, it tears a hole in the fabric. And in that extreme warping, time itself gets distorted beyond recognition. This is where things get weird. So let's go back to our scenario. As you get closer to the black hole's event horizon, the gravitational pull gets stronger and stronger. For every meter you descend, the time difference between you and your distant friend gets more extreme. To your friend, you appear to slow down, getting redder and dimmer until you just seem to freeze on the edge of the event horizon. Forever. They'll never see you cross it. But from your perspective, time is ticking away normally. You don't feel like you're in slow motion. You'd cross the event horizon in a finite amount of time, looking back to see the entire future of the universe unfolding in front of you. This effect is known as gravitational time dilation. The stronger the gravity, the slower time passes. Right at the event horizon, from an outside perspective, time essentially stops. This leads to a fascinating thought experiment. Could you use a black hole as a time machine? In a way, yes. You could orbit a supermassive black hole for what feels like a few years to you, then return to Earth to find that centuries, maybe even millennia, have passed. You'd have effectively traveled into the future. Of course, the practicalities are a nightmare. You'd need a spaceship that could withstand the insane gravitational forces. You'd have to avoid being ripped apart by tidal forces. But theoretically, it's a one-way ticket to the future. But what about the past? This is where physics gets even more speculative. Some theories propose that inside a rotating black hole, known as a Kerr black hole, things could be different. The singularity isn't a point, but a ring. These theories suggest that it might be possible to pass through this ring without being crushed, potentially emerging into another universe or another point in time, maybe even the past. This would involve what's called a closed time-like curve, basically a loop in space-time that brings you back to where you started in time. It's the stuff of science fiction, and most physicists are highly skeptical. Traveling to the past opens up all sorts of paradoxes, like the grandfather paradox, where you go back and prevent your own birth. The universe seems to have laws in place. like the chronology protection conjecture, that prevent this from happening. So, are black holes portals through time? For a one-way trip to the future, it's a solid maybe. For a trip to the past, the jury is definitely still out. But what's undeniable is that these cosmic behemoths force us to confront the true nature of time, not as a simple, constant ticking, but as a dynamic, warped, and mysterious part of the very fabric of our universe. What do you think? Let's go back to that opening scenario. You're approaching a black hole while your friend watches from a safe distance. As you get closer, something really strange happens. From your friend's perspective, you start moving in slow motion. Not because you're trying to slow down, but because time itself is flowing more slowly for you. From your view, everything feels normal. 1 second still feels like 1 second. But for your friend watching you, your seconds are stretching out. What takes you 1 second takes them 2 seconds to observe, then 5, then 10. The closer you get to the event horizon, the more extreme this becomes. Right at the event horizon, time dilation becomes infinite. From your friend's perspective, you'd appear to freeze. They'd watch you approach the boundary but never actually cross it. You'd seem stuck there forever, slowly fading as the light from you gets redshifted into nothingness. But from your perspective, you'd sail right through the event horizon without even noticing. No barrier, no wall, just an invisible line in space. This is one of the strangest paradoxes in physics. Two observers experiencing the same event completely differently, and both perspectives are correct. That's how warped time becomes near a black hole. Now let's flip the perspective. Instead of your friend watching you, imagine you're near the black hole, looking outward at the universe. You glance up at the stars, and they're moving. Fast, really fast. Time is passing incredibly quickly out there, because if time is moving slowly for you, then relative to you, the universe is aging rapidly. If you hung out near a black hole's event horizon for what felt like an hour, then returned to Earth, you might find that decades have passed, maybe centuries, maybe even millions of years. You'd have traveled to the future, not by moving through time in some magical way, but by experiencing time more slowly than the rest of the universe. This is theoretically a real form of time travel. It's allowed by physics. There's no law preventing it. In fact, this was the premise behind the movie Interstellar. Remember the water planet scene? The crew lands on a planet near a supermassive black hole. They spend a few hours there. When they return to their ship, 23 years have passed for their colleague. That's not Hollywood magic. That's actual physics. Near a supermassive black hole, time really does slow down that much. So if you wanted to see what Earth looks like in the year 5000, you could theoretically do it. Find a black hole, orbit close to the event horizon for a while, then come back. You'd arrive thousands of years in the future, having barely aged yourself. The catch: it's a one-way trip, you can't go back. But what about traveling to the past? That's where things get really weird. So far, we've been talking about simple, non-rotating black holes, but most black holes in the universe actually spin fast. When a massive star collapses, it's usually rotating, and as it collapses, conservation of angular momentum makes it spin even faster. The result is a rotating black hole, called a Kerr black hole. Rotating black holes are different. They don't just warp space-time, they drag it around with them. This creates a region called the ergosphere, where space itself is being pulled along. And here's where physics gets absolutely bizarre. Inside the ergosphere, something called closed time-like curves might exist. What's that? It's a path through space-time that loops back on itself. A trajectory where you could theoretically return to your own past. Let me put that in simpler terms. Near a rotating black hole, space-time could be warped so severely that it loops back on itself. You could travel in a circle through space and time and end up in your own past. This isn't science fiction. This is a legitimate solution to Einstein's field equations. The math checks out. But before you start planning your trip to fix past mistakes, there are massive problems. The paradoxes alone are enough to make your head spin. And that's not even considering the immense physical challenges of surviving such a journey. So while the theory is tantalizing, we're a long way from booking our trips back in time. What do you think? If you could travel to the future, would you take the one-way ticket? Let me know in the comments below. Up to now, we've mostly been looking at simple, non-rotating black holes. But here's the thing. Most black holes in the universe aren't just sitting still. They're spinning, and they're spinning fast. Imagine a giant star, thousands of times bigger than our sun. It's already rotating, just like a planet. When this star runs out of fuel and collapses under its own gravity, something incredible happens. Think of a figure skater pulling in their arms to spin faster. The star does the same thing, but on a cosmic scale. This conservation of angular momentum makes the collapsing core spin at mind-boggling speeds. The result is what we call a Kerr black hole, a rotating black hole. Now, these spinning black holes are a whole different beast. They don't just warp space-time, they actively drag it around with them, like a spoon stirring honey. This creates a fascinating region called the ergosphere. Inside the ergosphere, space itself is being pulled along at incredible speeds. If you were in a spaceship there, you would be forced to move with the rotation, even if your engines were firing at full power in the opposite direction. You couldn't stand still relative to a distant star. And this is where physics starts to sound like pure science fiction. Inside this swirling vortex of spacetime, some theories suggest that something called closed time-like curves could exist. What on earth is that? Well, it's a path through spacetime that literally loops back on itself. It has a trajectory where you could theoretically travel through time and space and end up right back where and when you started. Let me put that more simply. Near a rapidly spinning black hole, spacetime might be so severely twisted and warped that it actually folds back on itself, creating a loop. If you could navigate this loop, you could travel in what seems like a circle through space, only to arrive in your own past. This isn't just a wild idea from a movie. It's a legitimate mathematical solution to Einstein's field equations. The math actually works, but hold on. Before you start drawing up plans to travel back in time and fix your past mistakes, we need to talk about the massive, and I mean massive, problems with this idea. First off, let's talk about survival. The gravitational forces near a black hole are utterly extreme. Long before you could get anywhere near a time loop, these forces would tear you apart. Scientists have a wonderfully descriptive name for this process: spaghetti. The gravitational pull on your feet would be so much stronger than the pull on your head that your body would be stretched into a long, thin strand of atoms, like a noodle. Not exactly a pleasant way to go. The second major hurdle is the issue of causality paradoxes. If you could travel to the past, what would happen if you did something to prevent your own time travel? This is the famous grandfather paradox. If you go back and stop your grandfather from meeting your grandmother, you would never have been born. But if you were never born, you couldn't have gone back in time to stop them in the first place. It creates a logical loop with no solution. Some physicists believe these paradoxes are a clear sign that time travel to the past is fundamentally impossible. They argue the universe has built-in rules to prevent it. Others have different ideas. Maybe traveling to the past creates a new, branching timeline, a parallel universe. Or perhaps the universe is self-consistent. Whatever you do in the past has already happened and is part of the history that led to you traveling back in the first place. You can't change the past because you're already a part of it. And the third, and perhaps biggest, problem is that we have no idea if these closed time-like curves actually exist in the real universe. The math of general relativity says they could asterisk, but we've never observed anything like them. It's possible that when we finally develop a complete theory of quantum gravity, a theory that unites gravity with the weird rules of the quantum world, we'll find that these time loop solutions are actually impossible. General relativity is an amazing theory, but it's not the final word. The true nature of reality might have safeguards against time travel that we haven't even discovered yet. So, for now, the past remains safely in the past. So, you've decided to take the ultimate plunge and jump into a black hole. What actually happens? The answer is both more boring and way more terrifying than you might imagine. First, it depends on the size of the black hole. If it's a smaller stellar mass one, you're out of luck. The intense tidal forces would stretch you into a long, thin strand of atoms, a process charmingly called spaghettification. Long before you even reached the edge, you'd be cosmic spaghetti. But let's say you're smart about it and pick a supermassive black hole, like Sagittarius A** at the center of our galaxy. Here, the tidal forces are much gentler at the edge, so you could actually survive crossing the event horizon. From your perspective, it would be completely undramatic. You'd just float past this invisible line. No alarms, no flashing lights. It's just empty space. But then, you'd start to notice some weird stuff. If you looked back, you'd see the entire future of the universe playing out in fast forward, all compressed into a tiny, shrinking circle of light. It would be like watching cosmic history unfold in an instant. Looking forward, toward the center, space itself would get increasingly warped and twisted. But here's the truly mind-bending part. Once you're past the event horizon, the singularity is no longer a place in space you're heading toward. It's a moment in your future. It's as inevitable as next Tuesday. You can't turn around. You can't stop. Every possible path you could take, every direction you could move, ends at the singularity. It's not a destination. It's an appointment you can't miss. And what happens when you finally reach that appointment at the singularity? Well, that's where our science hits a wall. The laws of physics as we know them, Einstein's theory of general relativity, they just break down completely. The math gives us infinity, which is basically physics speak for we have no idea. To understand what's really going on, we need a new theory, a theory of quantum gravity that can merge the world of the very big with the world of the very small. Some theories speculate that the singularity isn't a single, infinitely dense point at all. Maybe it's a chaotic mess of quantum foam. Other or more wild theories suggest it could be a gateway to another universe or even a white hole, the theoretical opposite of a black hole, spewing out matter and energy. The truth is, we just don't know. And we probably won't know for sure until we finally unite quantum mechanics and gravity. Now, let's wrap this all up by talking about the craziest consequence of black holes: time travel. Black holes literally bend the fabric of space-time, and that means they bend time itself. The closer you get to that event horizon, the slower time flows for you compared to everyone else. This is called gravitational time dilation. If you could hover just outside the event horizon for, say, a few hours, you could return to Earth to find that thousands or even millions of years had passed. You would have effectively traveled into the future. It's not science fiction. It's allowed by the laws of physics. The technology to do it is way beyond us, of course, but it's theoretically possible. So what about traveling to the past? That's a lot more. Some theories about rotating black holes suggest they might create something called a closed time-like curve, which is basically a loop in time that could, in theory, let you travel to your own past. But we don't know if these are physically real or just interesting quirks in the math. The paradoxes they create, like going back and preventing your own birth, make many physicists skeptical. What all this really shows us is that our everyday understanding of time is just an illusion. It's not a universal clock ticking away at the same rate for everyone. It's a flexible, stretchable dimension that can be warped by gravity. Black holes are nature's time machines, at least for one-way trips to the future. They are cosmic laboratories that force us to confront the deepest mysteries of reality. So, here's my question for you. If you could safely visit the edge of a black hole, watch the universe age in a flash, and then return to Earth thousands of years in the future, would you do it? And what would you hope to see? Let me know your thoughts down in the comments. If you enjoyed this journey to the edge of time, make sure you hit that subscribe button. We're going to keep exploring the ideas that make you rethink everything you thought you knew. Thanks for watching, and I'll see you in the next one.